Sorry about the interruption. Let me go back to the example we were discussing, and I need to erase something here. I'm trying to find the eraser. I'm gonna have to erase this here. Well, it's not letting me erase that. So anyway, let's just deal with that. So it tells me that the observation well is 50 meters from well 1, and then it's 64 meters from well 2. So this is the distance from well 1 to the observation well that we call 0, and then this is the distance from 2 to that observation well. Then we have a second observation well, and this is observation well 2, and it tells me that the water table here measured at this observation well is 32.9 meters, and it's telling me that it's located 20 meters from well 1 and 23 meters from well 2. So this distance here would be R1, and this would be R2. Okay. What is important? I mean, you could have it reversed, but you need to be consistent with your notation. Okay. So let's now substitute in the equations. We need to determine the aquifer permeability. So we're using this expression. And now I have all the variables that I need because I put them in my sketch, which is very important. Okay. And if I use my observation well 1 as this value here, and my observation well here, then I have the distances. So really what you have are two observation wells, and you know what are the water tables for each one of those wells, and then just substitute in the equation. So we have, and again, I'm not going to solve the equation, just leave it expressed. So 32.1 squared is going to be equal to 40 squared, and then Q1, which is 3,000. And then I want to point out here that I'm leaving it at 3,000 cubic meters per day. If then your permeability has to be in meters per day. Okay, so you have pi k, and then the natural log, and then R10B, which is 50, and R1, which is 20, minus, and then for 2, we have 500 cubic meters per day, pi k, and then natural log, and then R2B, or R2 0B, which is 64, and then we have R2, which is 23. Okay, so you'll have to solve for your k value, and then again that is in the book. So now we're going to talk about steady flow in confined aquifers, and then again we'll use the same equation as before, Darcy's equation, plane polar coordinates as well. But now the thickness of the confined aquifer is B. And you can see here B. So this K times B, we call it the coefficient of transmissivity. So you'll see it sometimes separate, other times just as a T. So this would be the equation that you use for confined aquifer. You need to know it. And here is the thickness of the aquifer, and everything else is pretty much the same. Okay, so we have the HW, RW, and then the Q, which is the flow rate. So everything else is just like in the unconfined aquifer. Okay, so remember what I mentioned, we can have it separated, and in the book they go through the exercise of giving it to you instead of water table with the drawdown, so you can have the drawdown as well. And remember, the transmissivity in a confined aquifer is really the thickness times the coefficient of permeability. So these are the two equations that you would be using. You have two observation wells. So let's do that example. And this is a discharge for a confined aquifer. So that's the first thing you have to make sure you see. Okay. And let's see what we have. We have Q equals 2,500 cubic meters per day. And the aquifer transmissivity, so the T is 1,000 cubic squared per day. Because remember, if you have K feet per day and B feet or meters per day and times feet is then squared per day. The steady state drawdown measured at a distance of 60, so that drawdown at 60 meters is going to be 0.8. And the question is to determine, so this would be at R equals 60 meters. So we need to determine the drawdown at a distance of 150 meters. So this is 150. So defining those variables is what is really important. And so whenever we look at this, any well where you know the distance and the drawdown and the distance, or the distance and the water table, it would be like an observation well. So this would be your observation well of 0.8. Here you have your Q, and we'll leave it in cubic meters per day because the coefficient of transmissivity is in square meters per day. So you have here 2,500, and then the coefficient of transmissivity, and then the distance for that well here is 60 meters, and then we're going to calculate the drawdown at this distance. Okay, so that's what's the most important thing here. In this case, when we solve it, you should get a drawdown of 1.16 meters. So I encourage you to solve it, pause and solve it, and make sure you get that answer. This is for multiple wells, and this is for confined wells, and this is the giveaway that tells you that it's a confined well. So I want you to look at example 7.3 in page 261. This is the example, and study it on your own. And these two problems you need to turn in at the end of the class.